This last tutorial on the FEAT interface will cover the post stats and registration tabs. Post stats refers to how do you want to correct for multiple comparisons and visualize your results after you've carried out your analysis. For example, this first field here, pre-threshold masking, will allow you to select regions based on a priori hypotheses about where you should see activation. So for example, if you have a specific hypothesis about the visual cortex, you might want to select a mask that only restricts your search space to voxels within the visual cortex. This has the benefit of restricting your search space and therefore reducing the number of multiple comparisons you have to correct for, thus boosting your statistical power. Now there are different thresholding mechanisms you can use to visualize your results at each voxel. This first one, uncorrected, doesn't apply any correction mechanisms. It simply looks at each voxel on a voxel by voxel basis and looks at whether it passes a certain P threshold. The next option, voxel-based correction, will apply a sort of Gaussian random fields correction to each voxel. This is more conservative than, say, the uncorrected test, but will allow you to correct for multiple comparisons at the voxel level. This last option is called cluster. What it does is after Z-maps are generated, which specifies a Z-value at each voxel in the brain, it then looks at whether any clusters of these voxels at a Z threshold of this value, specified here, or greater, can appear at this percent of the time by chance or not. So for example, given a certain amount of contiguous voxels which pass a Z threshold of 2.3, we can see whether that particular cluster would be observed 5% of the time by chance if the null hypothesis were true, that there is no activation. Here, this contrast masking allows you to specify a mask based on another contrast. So for example, I could say that I want to mask any one of these contrasts with any other contrast. So for example, I would only want to see what voxels are active in contrast 6 based on which voxels pass a certain threshold based on a contrast 3. Lastly, rendering allows you to specify how you want to look at these activation plots on an actual brain. For example, do you want solid blobs or transparent blobs? And this create time series plot down here will allow you to see a time series plot of peak voxels and compare this to the actual model fit, which we will see later. And finally, we come to the registration tab. Now, registration and normalization are carried out last in FSL because of any potential spatial correlations they can introduce into the data before you carry out a statistical analysis. So there are two different things, two separate steps going on in this registration tab. The first one is co-registration. This refers to aligning all of your functional images into the same orientation and roughly the same space as your anatomical image. Then, normalization refers to warping your anatomical image to a standardized space, such as TallyRack or MNI, and then applying these warps to the functional images that were realigned to your anatomical image. So the two things we need here are this main structural image and a standard space. First, the main structural image. What we need to select is the anatomical image that has had all of the non-brain matter removed from it. So for example, after we ran our BET tool on our anatomical image, which is S007, we got this image with an underscore brain suffix appended to it. So let's go ahead and select that. Standard space refers to what template do we want to warp to. And there are several different templates provided in this user local FSL data standard directory. Here a default is filled in for us and will work well enough for our purposes. This is an MNI brain, which stands for Montreal Neurological Institute, and it's being resampled to 2 millimeter isotropic voxels. Lastly, these search spaces will allow us to specify more full and comprehensive searches. I'm going to go ahead and select them and increase the degrees of freedom for what it searches for, because a more comprehensive search, although it increases computational time and cost, can result in a better fit when you co-register and normalize your images. This nonlinear option will apply nonlinear warp when warping to a standardized space, which can be slightly more accurate, but can result in very, very high computational time. So I'm going to leave it blank for now. After we've done all that, I'm going to go ahead and click on this Save button here. This allows you to save an FSF file. And what this will do is it will allow us to save everything we've done in a text file so that we can then run it later and load it if we need to. So here I'm just going to call this analysis.fsf and hit OK. Alright, so now we've finished everything that's in the FEAT interface, and now you can go ahead and hit Go, and in the next tutorial we'll cover all the different HTML pop-ups that occur to track your progress.